Three main factors are there which affect the thermodynamic stability. One, nature of metal, second, ligand, and third, ring formation or alignment or arrangement of the ligands. Out of the nature of metal, we discussed one time. Only one portion was left, class A and class B kind of metal, that we covered later on. That nature of metal is with the 3 points. What are the 3 points under the nature of metal? First point,
Size and charge.
yeah, means charge density. Second point,
Crystal field effect.
CFE. And third point,
Class A and B
yes,
metals.
category of the metal. And about the nature of the ligand or the coordinating group, which points were there? First point,
Base strength.
yes, basic strength of the ligand. And this point is related to the ionic bonding. Second point,
Covalent bond.
yes, covalent bonding means covalent character is this related to the ligand. And the third point,
Concentration.
right, concentration of ligands. So these two aspects we discuss. Now I discuss the ring formation or the ring structure. For that, we should know one term that is called a chelate or chelation. What are the ring structure compound remains, means coordination compound I am saying, metal ion remains one of the member of the ring. Then such ring structured compounds are called as chelates. And what is noted, the chelates are extra stable, extraordinary for stability. For example, if I consider say zinc can coordinate to four ammonia molecules. It's a one ammonia molecule, second ammonia molecule, third ammonia molecule, and fourth. Let me represent that the ammonia. Ammonia means NH3. One mistake I did. What is that?
Zm.
Good. Yeah. It's a zinc. Zinc plus 2 I want to consider. So will anybody help me? What can be the charge on this complex ion? Think about the charge on zinc possible, charge on ammonia, and summation of those charges, oxidation state of the first transition series, metal ions you have discussed. Few compounds are zinc you might be knowing. So what's the possible oxidation state for the zinc? Only one oxidation state is possible here.
Plus 2.
Right. So what is the charge on this complex?
+2.
Plus to right. So it is a monodentate ligand possessing complex. It is not a ring structured complex. But in spite of this ammonia, if I consider ethylene diamine as a ligand, ethylene molecule means CH2 double bond, CH2 remains, but one addition is there. There NH2 group is added, so single bond remains there, and here NH2. So in ethylene, two amine groups are added. So it is called as ethylene diamine. And this nitrogen is a donor. This nitrogen also is a donor. Total two donating species or donor species are there in ethylene diamine. Central metal, let me consider as is there before, that is what zinc. And this ethylene diamine, one NH2 through which it links, and second NH2 through which other linkage will be there, means coordinate bond will be there, and between this NH2, CH2 and CH2, it is our ethylene diamine molecule. Similarly, I represent the other ring. Other ring means ethylene diamine only, one NH2 and second NH2 through which linkage occurs. But between this NH2, a joiner is ethylene or CH2 and CH2. So here also coordination number is 4. Coordination number 4. Here also coordination number is 4. But this structure, right hand structure, is ring structure. Right hand side complex is chelate. Why I am saying ring structure? Because you could able to understand zinc is one of the member in the ring. Nitrogen is a second member. Carbon is a third member. This carbon is a fourth member. And this nitrogen is a fifth member. So it is a 5-membered ring. Similarly, here also 5-membered ring is there. Now I don't want to bring your attention to the number of members. Only I want to emphasize presence of ring. That ring is not present in the first structure but is present in the second structure. Such ring structure compounds are called as chelates, or the process of bonding by means of these ring structured ligands, possible ligands which can form the ring structure, is called as chelation. Is that concept clear?
Yes, sir.
Yes. I said the chelates are extra stable. Chelates are extra stable. Question arises, why? why are they extra stable? So that explanation I provide to you. So what is chillet effect? In that, what is meant by chillation or what is meant by chillet, that you have to answer. You have to provide the example. I said that zinc ethylene diamine complex, where coordination number is 4, is more stable than simple monodentate complex formed by the ammonia as a ligand ZnNH3 4 plus 2. So this is the chillet effect, and this more stability is to explain. If you go to the book, then you will find the stability constants also. Log K value. K is a formation constant, stability constant for this ethylene diamine complex is 11.07, and stability constant, that is expressed in terms of log, is 9.46. Question you will be with, why that term log is there? See, we use the term log for our better understanding. If I have to talk about the concentration of hydrogen ion, that concentration which remains 10 to some power. If that power is negative, then negative log is taken, and that negative log is called P, power of hydrogen ion. Here negative log is not needed because that power of 10 is positive. So simple log term is given. So log is such a function which makes the number simple. Instead of saying 2.1 into 10 raised to minus 19 as a concentration of H plus ion, directly it will say the pH. Actually 19 is not possible there because 10 to minus 14 is a total ionic fluid. So 10 to minus 13 you can say. But here the stability constant, see 10 raised to 7, 10 raised to 9. Likewise possibilities are there. So in spite of expressing one number into 10 raised to that, it is better to express in terms of log. So only for the sake of representation, log term is given. But anyhow, it is representing the stability. Stability of ethylene diamine complex is more than that of the zinc ammonia molecule. Try to remember this number. For ethylene diamine, stability is more than 11. 11 cricket players. 11.07. That 07. That number you can remember. Maybe James Bond you can remember, Mahendra Singh Dhoni you can remember, or other player also you can remember. So 11.07. And for zinc ammonia complex, it is 9 point numbers which summation is what? 10. But cricket main points 4 and 6. 9.46. So it is just the playing with that the number is a stability constant. So you can compare, and statistical presentation will help you to make your answer more impressive, especially if it's a descriptive. And if it's a MCQ kind, then for comparison, if you know few data, then it will help. And it's an interesting, enjoyable process. That's the memorization. Now, main point is chelates are stable. Why? Stability depends on what? Bond formation. Bonds are between whom? Metal and ligand. By any means, by thermal means, by heat or by other purposes, this bond will become weak, and that bond can cleave or bond can break, and ligand will go out, metal will. So metal and ligand will separate. Easy separation means less stability, or difficult to separate means more stability. So more and less stability. Student, just a wait. Yes, Advait or Sachin. Advait or Sachin, please close the door. Yeah. As easily a bond gets break or bond cleaves, bond dissociate, less will be the stability. So what is happening in case of the monodentate ligand complex? Bonds are easy to break. Or what is happening in case of the chelates? Difficult to rupture the bond, difficult to break the bond. Now I have to answer, why is it difficult to break the bonds? Just imagine one chelate, say the ethylene diamond complex, metal was there, so Zn plus 2, and it was linked to the ligand. So such kind of the structure was there. Such kind of the one ring was there. Here there was what? The other ring. I want to bring your attention to only one ring. Say, if I have to rupture the bond between the ligand and, here ligand is there, ligand and metal, I have to work more because I have to break the two bonds. Two times I have to work. And by any means, suppose if one bond breaks, here one bond breaks, then other bond will be there. And due to that other bond, that ligand will remain hanging. Ligand will remain. Chances are there the broken bond again can form. So simultaneous breaking is a one thing. Simultaneous breaking may not be possible. One bond broke, so we felt as if like ligand went out. No, ligand will not go out because other bond is there. And before breaking other bond, little chances are there original bond will form. Means what? If I break this bond, you will find because of other bond ligand is intact. And before breaking that other bond, chances are there broken bond can again form. So too much efforts we need to pay to break the bonds. Difficulty in breaking the bond is numerous or more in chelates or chelate complexes. Therefore, they are extraordinary for what? Stability. Extra stability of chelates can be explained by this reason. It is just a qualitative reason. It is not the perfect reason, but for understanding that will help. Are you understanding this first reason why chelates are stable? Waiting for your replies. If no, then say no.
Question not clear, sir.
Listen carefully. What I was asking, whatever I taught to you about the extra stability of chelates due to multiple bond existence, breaking those bonds simultaneously is a tough task. In case one bond breaks, other bond can establish. Is this point clear? That is my question.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now, second point. It is a perfect point. It is a quantitative explanation. An answer of stability lies in thermodynamics. That's a Gibbs equation you might be knowing. Delta G is equal to, yes, at least complete now.
S.
S.
Right. S for what?
Entropy.
Yes, and this term is very important for us. Entropy change. And what's the logic? If delta G is negative, more negative, what will be the consequence? Consequence will be the more stability or more favorable that reaction will be. What we want? Delta G should be more negative. When can this term be more negative? If delta H is less positive. If this term T delta S is high, more and more, means of course positive, then delta G will be more negative. Means temperature also should be high. Therefore, at elevated temperature, at high temperature, speed of the reaction, rate of the reaction, tendency of completion of the reaction increases. But our main point is this delta S. In order to make that term T delta S large, delta S also should be large or more. Entropy change should be more. Higher or larger the entropy change, more will be the stability or more easily that reaction will occur. So my point of interest here to discuss is entropy change, that is delta S. For that, let me consider two reactions. One reaction where monodentate complex are there or ligands of monodentate, ligands of nature are in the complex, and other chelate is there. Or from monodentate, how to obtain that the chelate, that let me what the discuss. If I consider say nickel complex, nickel aquo complex, octahedral complex, NiH2O6 plus 2, basic should be there with you. Nickel can carry the plus 2 charge. And if I add ammonia molecules in this, and number of ammonia molecules time being considered 2 only I am adding. Stepwise, then the reaction will be with the product NiH2O4 and 2 ammonia molecules which are newly added, charge will not change, plus 2 plus 2 water molecules which are displaced before. This is our reaction. One more reaction I write here, which is of our most interest. Both are important reactions for understanding purpose. Here I want to consider chelate complex. Again, let me consider nickel aquo complex. Of course, octahedral complex. And in spite of ammonia, let me consider En, ethylene diamine. It is a bidentate ligand. Two donor atoms are there. And that's the reason I consider upside two ammonia molecules. Two donors I want therefore. So what will be the product? Nickel and two water molecules will be displaced. So 4 will be left and one ethylene diamine will be there. Charge will be plus 2 plus 2H2O. Reaction seems to be simple, but I said as before, our point of interest is entropy change, delta S. So how to find that entropy change? What is that entropy? Yes, anybody knows what entropy is a measure of? Entropy is a measure of.
Randomness and situation.
Right, entropy is a measure of randomness. In nearly all books, this word remains randomness or or disorder, no proper arrangement, no proper alignment. Means when teacher remains, suppose if you are in the classroom and teacher is teaching, then at that time you will sit at your place. You will be attentive. As soon as teacher leaves the classroom, what are the more chances? You will not remain at that place. You will change your place and you will not be with that alert position. You will shift your what the position. What is that disorder? What is that randomness? Randomness, why it is said one can pay attention to the board, teacher is not there, but we'll see just board. One will see out of that window, one will see other where, one will turn and will gossip with the other friends. So everybody's direction will be different, which was uniform when teacher was present. So that non-directional thing, that's a random behavior, random alignment, random arrangement, that is a disorder. More the disorder, more will be the entropy change. One more example I give it to you. It is said entropy of the universe is increasing. Just take a drop of the petrol or the diesel or the fuel. As you burn that drop, as you use that drop, as you use it as a fuel, what happens? When oxides of carbon and plus other sulfur, nitrogen may partly what evolve. Oxides of carbon do evolve. Previously there were few molecules and now are many. Increase in entropy. When many remains means disorder is there. To make concept of manyness, one more example. If we consider a tree, that tree is formed from what? Yes, how the tree grows. What is the proper reason for the growth of the tree? Yes, tree grows due to which process? Consider bark tree, large tree, any tree if you consider the same thing, or plant even if you consider what remains there, which process by which food is prepared.
Photosynthesis.
Yeah, and as per the coding, the type of the bark will be there for what the that's a photosynthesis. That tree is grown, and for photosynthesis, what is used? What is the need for photosynthesis? When photosynthesis occurs, which gas? At least complete now. Which gas for photosynthesis remains or used?
Carbon
Carbon
dioxide.
dioxide. Yes, CO2 and what is needed for photosynthesis? CO2 and at least complete
Water.
now. Water. In presence of photon, they will combine and will form carbohydrate. That's a food. It's a photosynthesis reaction, and which are where necessary, it is used for the growth. So carbon dioxide from air, moisture means maybe the water supply, that those are brought together. See, it is a very interesting. Separate carbon dioxide molecules were there and water molecules were there. They brought together. Here there's a discipline. Here coagulation is there. Here ordered. They are ordered now. They brought together. It is opposite of entropy increase, or there's a decrease in entropy you can say. But if you burn that wood, again that carbon dioxide and moisture will come out. There is increase in entropy. One tree is there, and that tree you will cut in various parts, small wood parts, wood blocks. So that small wood blocks are there. Previously all were united, all were together, but now they are more. There is increase in entropy. One more example I give it to. It's a very interesting and important concept, entropy. If I consider one book, notebook, or textbook, and consider that all pages remain intact. Why? Because binding remains. Book remains with binding. Suppose if I remove that binding, if I cut that binding, and if I keep that all pages there on the table, and if I come tomorrow or after a few days, what may I find? All pages will not be on table. They will scatter here and there, maybe because of wind or other means. When you remove that bindedness, manyness occur, and that manyness is a measure of disorder. One tree from that many small blocks of the wood, manyness. One drop of the petrol or diesel or fuel, or one molecule of the fuel and many molecules. Yes, students, are you understanding what I am saying about the entropy change?
Yes, sir.
Yeah. Now let us find out whether there is a manyness or lessness. Means manyness means increase in the molecules or decrease in the molecule, or molecule remains same. And where there is a more increase, there is a more increase in entropy. And we want the entropy should increase. We want more delta S. Why? For delta G should be more negative. Why delta G should be more negative? We want favorable reaction. We want stability. Or we want to consider or measure stability. Here, how many entities are there? How many species are there? How many molecules are there? Here is only one molecular ion. Here, two are there. Similarly, to this reactant side for second reaction, one, and here there is a one. So if I do the total here is three. Three reacting species are there, and total here is two. Two reacting species are there. In first reaction, three reacting species, molecular ions, and second reaction, only two are there. Now let us think about the product. Here there is a one molecular ion, and here there are two. So if I sum up, how much will be that we can find out. Here there is only one molecular ion, and here there are two. So if I sum up now, combination of these two, how many species are there? Three. Combination of these two, how many species are there? Three. Now pay attention. What is happening in the first reaction? Three were there to left side, three are there to right side. Three were there to reactant side, three are there to product side. But for second reaction, two were there to reactant side, but three are there to product side. Could you able to understand? Two to three. Two molecules were there at reactant side and three are there to product side. What do you think? Where is there increase in entropy, in first case or in second case?
Second.
Yes, absolutely. So because of increase in number of species, entropy change will be more. More the entropy change, delta G will be more negative. More negative the delta G, more favorable reaction will be, or more stable resultant compound will be. Therefore, our interest was to the entropy change. So here by reaction and by measuring the number of entities or the species, I taught you increase in the entropy occurs or happens in chelate formation. Therefore, chelates are stable. So two reasons so far I had given to you for chelate stability. One reason, simple, it's a qualitative reason, and that qualitative reason is about, yes, number of bonds and breaking or cleavage of the bond. And second reason is quantitative, and that is related to change in the entropy. Yes, is this point clear? Yes or no?
Yes, sir.
Yes.
So we studied now what is meant by chelate or chelation. Chelates are stable. Why? Two reasons. One, qualitative, and other quantitative. That's a portion I covered till now. Now I want to go to the further refinement. Among chelates, who are more stable? Now only I was talking about chelates and monodentate complexes. But if I consider chelates only, then among chelates, who are more stable? For that, two factors are there. One factor, number of members, and other factor, number of rings. What is found? Higher the number of rings, more will be the stability. Higher the number of rings, more will be the stability. And about the number of members, it depends what kinds of ligands are there. Generally, 6-membered, 5-membered ligands are more stable. This is general point of. But here let me cover the first point, number of rings. And what is my statement? Higher the number of rings, more will be the stability. And that is the reason why EDTA complex. Have you heard this name, EDTA?
Yes, sir.
These EDTA complexes are more stable, or these EDTA titrations help us to estimate or determine metal ion quantitatively. So to make this concept clear of increase in the, means what is happening in case of EDTA complex, number of rings are more. Now how the number of rings can increase with such giant molecule? Means when many such things are there and the ring formation, and only one thing and ring formation, then number of rings what increases. To make this concept clear, I give you the one example. Say the copper plus 2 complex. Two ligands, let me highlight here. I want to know the answer from you. What's the name of this ligand? I told you already while discussing chelate effect. Ammonia complex and this ligand complex was considered. What's the name of this ligand? It's a short form of that.
Amine.
No, no. Amine means NH3. I said no, EN is a representation for that. Z and EN twice. What is this? An addition of to amine. What is this? Means here.
Ethylene diamine.
Right, ethylene diamine, one ethylene molecule, two amine molecules. Otherly, I want to consider a trine molecule, means three ethylene diamine. Three ethylene, sorry, not three. Three ethylene will be there and four amine will be there. Means how can I represent that? It's a one NH2, second NH2, third NH2, and fourth NH2. So such 4 NH2 or NH. It depends in linkage because nitrogen is a trivalent, no? So when it remains at end, NH2 will be there. But if it remains in between, then there will be what? NH. And now the linkage between them. I represent it by what? The black color. Carbon. Ethylene we have to consider. So let me consider here ethylene CH2 CH2 and here is a linkage. Here CH2 CH2 ethylene and here is the linkage of addition. Again CH2 CH2 and here is a linkage. So how many ethylene are there? 1, 2, 3. Therefore tri. And how many amine are there? 1, 2 amine or related derivative. 3, 4. So triene is a formula. So what is the coordination number for this ligand? What is the denticity for this ligand? Ethylene diamine. Denticity. Denticity means number of bonds, number of dents, number of teeth. Teeth means donors. These donors are there, no? They do bite the metal, bite. So how many bites are possible for ethylene diamine? That is called as denticity. What is the denticity for ethylene diamine?
two,
Now, how many bonds one ethylene diamine molecule can form with the metal ion? How many coordinate bonds? Here, how many bonds are represented? Amine group is a donor group. How many amines are there?
two,
Two.
four,
Diamine, two is a denticity. And what about the second ligand? Triene, triethylene, tetramine. So what will be the denticity?
four,
Right, 4. So through this nitrogen bite possible, through this nitrogen bite possible, through this nitrogen bite possible, through this nitrogen bite possible. We want to count the stability. We want to count the number of rings. So where there are more number of rings, that complex will be more stable. But coordination number should be same. The metal ion that I want to consider here is Cu plus 2. Two options are there. One, complex with ethylene diamine. So ethylene diamine is with what? Two amine groups and in between CH2 CH2. It's a ring. Coordination number 4. So NH2 NH2 and it's a CH2 CH2. So total how many ethylene diamine I had considered here? What's the formula? CuEn. How many ethylene diamine are there in this molecule? Yes,
two,
what's up? Ethylene diamine, how coordination number is 4. Number of bonds are 4. Number of coordinate bonds are 4. But how many ligands are there?
two.
Only 2. It's a one ligand, it's a second ligand. Are you following what I'm saying?
Yes, sir.
Yes. And other example is triethylene tetramine. How can I represent that? Here one NH2 is there. And here last NH2 you can consider. And between here is what? An H. And here is what? An H. And is NH2, NH, CH2, CH2 is there in between. NH, NH, CH2, CH2 is there in between. NH, NH2, CH2, CH2 is there in between. How many bonds it can form? That's our interest. 4. So coordination number is 4. But my question here is how many rings are there? Here ligand is only one. One ligand. So formula will be Cu trine Trien triethylene tetramine. Sorry, only one ligand. Only one ligand. And charge will be plus 2. But our point of interest to find the number of rings. How many rings are here? In the first case, 2 rings are there.
Two,
Two rings are there. Two rings here in first case. In second case, how many rings are there? How many are there?
three,
Good, good. I was expecting how many can answer 4 because I was attempting to write 4. There are 3 rings. Which are those? Here is a first ring. Here is a second ring. And here is a third ring. Number of members if I have to find out. Metal ion is the first. Nitrogen from amine is second. Carbon third. Carbon from other carbon from that ethylene is a fourth. And this NH is fifth. Nitrogen from NH is fifth. So it is a 5-membered ring as is here in case of ethylene diamine. 5-membered, but number of rings. Here 2 rings are there and here 3 rings are there. As per my previous statement. What was my previous statement? Higher the number of rings, what will be there?
higher the stability.
Right, more the stability, higher the stability. Accordingly, you will understand a ligand like EDTA, one EDTA, only one molecular ion, EDTA minus 2 also is represented. One EDTA minus 2 ion, one EDTA molecular ion forms 6 bonds, 6 coordination number. In case of trine, we found 4. In case of ethylene diamine, we noted 2. But but EDTA, ethylene diamine tetraacetate, form 6 kind of the bonds. Higher the bond formed by only one molecular ion, more will be the number of rings. Means if I consider say nickel complex, nickel ethylene diamine complex, octahedral complex, I need to consider 3 ethylene but if I have to represent the EDTA complex, then only one EDTA is sufficient. Only one EDTA ion is sufficient, which carries the -2 charge. EDTA carries the -2 charge. So nickel +2 and EDTA -2 gets what the cancel. So I not represent any charge on the complex. So here 3 were needed. So only 3 rings are possible. But here how many rings will be possible? Just guess. How many rings are possible by EDTA? 6 donors are there in one molecule. In case of trine, 4 donors were there, 3 rings were there. How many rings EDTA can form? Here 3 rings are possible in this complex. But if I consider EDTA, how many rings are possible? To help you, I am giving a logic. When I consider trine, 4 donors were there, 3 rings were there. Here 6 donors are there. How many rings will be there?
5.
Right, 5 rings are there in the EDTA complex. And because of such a large number of the rings, this EDTA complex is more stable, or EDTA complexes are more stable. Certainly more than monodentate ligand, even other chelates, other ring structure complexes, compared to them also, these ligands are stable. So students, today what I discuss, what is the first point? Concept of, which concept I discussed today?
Chelation.
Right, chilate or chilation. Second point that I covered, example also I inform. Third point, example which one? Zinc ammonia complex and zinc ethylene diamine complex. Of course, didn't carry the positive charge. And remember, there I committed one mistake while writing that the zinc. So with that also you can remember what point was covered. Then I answered the statement, why are such chelates more stable? And 2 reasons were there. One, qualitative, and other quantitative. Then I discuss in true sense actually the chelates. So 2 things are possible. One, number of rings, and second, members in the ring. Number of members in the ring. And out of that I discuss this first point, number of rings. Higher the number of rings, more will be the stability. About members, 5 or 6 membered chelates are more stable. When 5 membered and when 6 membered, that we will discuss next time. So students, let me know from you, is today's discussion clear to you?
Yes, sir.
Yes.
Yes, sir. Yes, sir.
Okay, shall we stop now?
Okay, sir.
Okay, if you have doubts as such, next time we can have the discussion. So I declare here today's session is over. Quit now.